yeah, so it's going to be 72 divided by 4, so the final current now is going to be 18 amps. All right, so, and then if we want to find the time constant, remember the time constant here, so the current through the inductor, IL, is going to be, I final plus I initial minus I final e to the minus t over tau, and in this case tau is going to be R over L. And this R is the R Thevenin equivalent. So we found the final current, it's 18 amps. We found the initial current, it's going to be 9 amps. And now we need to find the time constant. And to find the time constant, we need to find the Thevenin equivalent. The Thevenin equivalent is looking in from this terminal. So we can define the Thevenin resistance. We can basically set all of the voltage sources to 0 volts and the current sources to 0 amps. So that makes this thing a wire. And we look in and it's going to be, these two resistances in parallel with each other. So, so again, 4 ohms, so tau is going to be 4 divided by 100 microhenry. All right, so we come over here. Yep, this is exactly, we did this. This is just another way of thinking about it. We open up the circuit at this point, and then we want to find the Thevenin equivalent looking in. It's going to be 72 times 4. So the time constant then will be the 100 microhenry divided by 4, so 25 microseconds. So IL is going to be the final current, which was 18, plus the initial minus the final. So the initial, I guess, was 9 minus 18, so that would give you the minus 9. And then the e to the minus t over tau. Now, if we want to find so that's this current here. Now, if we want to find this particular voltage, the current basically gets split between these two 8-ohm resistance, or I guess we could think of the current running through the parallel combination of 8 ohms with 8 ohms. So the voltage is going to be IL times 8 in parallel with 8, which would be 4. So we're just going to take IL and multiply by 4, and that gives us the voltage at this terminal. All right, so there's example 3. Example 4, so again, the switch closes at time t equal to 0, and we want to find the voltage across the capacitor. So to solve these problems, we always want to find the initial. I guess I could write the formula here. VC is going to be the final voltage plus the initial minus the final, e to the minus t over tau. In this case, tau is going to be R Thevenin times C, because we're looking at the voltage across the capacitor. So when time t equal to 0, or before time t equal to 0, basically this thing is gone, and the capacitor is completely charged up. And so, one way you could think about it is you could do a source transformation here, and that's going to be 40 volts, 8 ohm on a resistor. And so the initial voltage, V initial, has to be 40 volts. Okay, then when the switch has been closed, okay, now this thing is closed, and it's like this 8 ohm resistor, these two 8 ohm resistors are in parallel, and so this becomes a 4 ohm resistor, and now the voltage is going to be, this looks equivalent to now 4 times 5, which would be the 20 volts, and then a 4 ohm resistor across the capacitor. So that this VF then is going to be 20 volts. All right, and then if we wanted to find tau, we need to find the Thevenin equivalent. And the Thevenin equivalent is going to be if we open up the capacitor and look into the circuit. So in this particular case, we can set the current source to 0 amps. So that basically takes this line out. And then we have 8 in parallel with 8. Gives us a 4 ohm resistor. So our Thevenin is equal to 4 ohms, from which we can get the time constant. Okay, and that's kind of what's going on here. You get the time constant. You have 4 times the value of the capacitor. So it's 400 microseconds. Time constants are in terms of seconds. So we're going to have the final voltage, which was 20, and then we have the final voltage was just 20, and then the initial minus the final. Did we do it right? Yeah, the initial is 40 minus the final is 20, gives us a 20 volts. So this is the value of the voltage through the capacitor. Now, if I wanted to find the current here, by the way, IC, what would I do? So IC is going to be C dV dt, dVc dt. So I would multiply the capacitor times, and I'm going to take the derivative. So I take the derivative of constant, I get a constant, and then this is going to be 20. And I'm going to have the e to the minus t over 400 microseconds, and then I'm going to multiply this whole thing by, a negative 1 over tau, so 400 microseconds. So, anyways, that's the voltage across, the current through the capacitor. Okay, here's another example, example 5. So in this particular case, when we want to find the current through the inductor, so we can write our formula. The current through the inductor is going to be the final current plus the initial, let's just call that IL. So the current through the inductor, I naught minus IF, e to the minus t over tau, and tau is going to be, in this case, R Thevenin divided by L. So we just need to find the final, the initial, and R Thevenin. So to find the initial current, we look at when time is, the switch has been closed, then because at time t equals 0, the switch opens. So the switch here has been closed for a long period of time. When it's been closed for a long time, you see this looks like a wire. So at time t equal to 0, we think of this as a wire, which basically cuts that guy out. And you say, what is the current? So we could basically do the Thevenin equivalent here. So we're going to get a current source with the 3 ohm, and then 30 ohm, and then 6 ohm, like that. And this current source would be 120 divided by 3. So what is that? 40 amps. And then we can combine 3 in parallel with 30. So we have 40 amps, 3 in parallel with 30. And that's and then we have our 6 ohm, and then, a wire. We want to find this current. And so now we could come back to a voltage source, and it's going to be 3 in parallel with 30, and then 6. And this would be, 40 times 3 in parallel with 30. Let me just look on my computer. All right, so 3 in parallel with 30 is going to be equal to 2.72 2.72, and when I multiply that by times 40, I get 108.8. Okay, so now the current that flows here, I0, is going to be 108.8 volts divided by 6 plus 2.72. So let's see, 108.8 divided by 6 plus 2.72. And I get 12.5 amps. Okay, so the initial current is 12.5 amps. Now if I go to find the final current, so in the final current, the circuit is open. Whoops. The circuit is open, right? And so what's going to happen, oh, and by the way, this is a negative. That's a negative 12.5 because the way we computed it was current coming in this direction, and the arrow goes in the opposite direction. So when once the switch is open, all the current is going to drain through this resistor and eventually drain off. And so the final current is going to be 0 amps. And then to find the Thevenin equivalent, what I'm going to do is I'm going to open this guy up. I'm going to open this up and think about the circuit looking in. And this 2 ohm is actually, oh, I guess this is, yeah, this is after it's opened up. So after it's opened up, the Thevenin equivalent, the only circuit is this guy. So the Thevenin equivalent, RTH, is just the 2 ohms. All right, so IL, then is going to be the final current, 0, plus the initial, minus 12.5, minus the final, 0, e to the minus t over tau, and tau is 2 divided by 8 millihenries, which is going to be, what, 0.25 I'm sorry, this is L over R. So this is 8 millihenries divided by 2, or 4 milliseconds. All right, so IL of t is going to be minus 12.5 e to the minus t divided by 4 milliseconds. All right, let's look at example 6. So again, when the switch is closed for a long time before t equals 0, and then at t equals 0, it switches open. So when it's closed, everything's going to charge up this capacitor, and then when it opens, the capacitor will discharge through the resistor. So again, I could write that the voltage across the capacitor is going to be the final voltage plus the initial voltage minus the final voltage, e to the minus t over tau, and tau will be equal to RTHC. All right, so we need to find the initial voltage. So when this thing is closed, okay, everything charges up. So basically, we will be charging up this capacitor. And basically, to find the that voltage, we want to turn, this guy is going to go on the other side, and we want to turn that all into a Thevenin equivalent circuit. So we could think of it as 7.5 milliamps, and then we're going to have 80 kilo ohms a series of 20 kilo ohm, and then 50 kilo ohm, and then we've got our capacitor out here, right? So we could do source transformations. So this is going to be plus or minus. So here we'll have 80 kilo ohm, and then we'll have 7.5 times 80. 7.5 times 80 gives me 600 volts. And then we still have our 20 k ohm and 50 k ohm and the capacitor. So we can combine those and get 100 and then do a source transformation back. So that's going to be, we're going to have a current source. We've got our 100 kilo ohm. And now we're going to have 600 divided by 100K. So that would be what? 6 millivolts? Does that sound right? 6 millivolts. And then we're going to have 50K here. And then we still have our capacitor. And then we're trying to find the voltage, the final voltage there. So we have 100K and 50K. And that gives us 6 millivolts, or milliamps, I'm sorry, 6 milliamps. And so we have 50 times 100 divided by 50. So this should be 33.3 kilo ohms. We have our capacitor. And then we do a final source transformation. 33.3 kilo ohm. And this guy is 6 milliamps times 33.3 kilo ohm. So 33.3 times 6 gives me roughly 200 volts. 6 times 33. Okay. So the that means that the initial voltage, V initial, is going to be 200 volts. And then we look at the final voltage. So after after this flip is switched at t equal to 0, the capacitor just discharges. So it'll discharge to 0. So VF is going to be 0 volts. And while it's discharging, the circuit while it's discharging, all it sees is 50 kilo ohms. So the R Thevenin is going to be 50 kilo ohm, which implies that tau is going to be RTH times C, so 50K times 0.4 micro. So that's going to give us, what, a fourth, 25, 12.5 milliseconds. So the voltage across the capacitor is going to be the final voltage, which is 0, plus the initial voltage, which is 200, minus the final, which is 0, e to the minus t divided by tau, which is 12.5 milliseconds. And this is in units of volts. All right, let's do this last. I've got another example, example 7. Okay, so this is a good example because we want to find both the voltage and the current through this, this inductor. So our formula for the current through the inductor is going to be IL is going to be I final plus I initial minus I final, e to the minus t over tau, where tau is going to be our L over R, Thevenin. And then to find the voltage, we would differentiate. So to find the initial current, so when t is before t is equal to 0, this switch is open and nothing happens here, and the amount of current is just dictated by these two resistances. So our I initial is just going to be, and we assume, of course, that this guy is a wire. So it's just going to be 20 divided by 4. So I initial will be 20 divided by 4, which is going to be 5 amps. Okay, now when the switch is closed, we basically bypass this 3 ohm resistor. So and again, we're going to assume as time goes to infinity, this starts looking like a wire. So now the current final is going to be 20 divided by just 1 ohm. So I final is going to be 20 amps. Okay, now when the circuit is closed, that's when we want to find the Thevenin equivalent. So this guy's closed, this guy's is basically not there. We look back in, what is the Thevenin equivalent resistance? It's going to be 1. So RTH is going to be 1 ohm, which means that tau is going to be 1 ohm times 80 millihenry. So it's going to be 80 milliseconds. All right, so the initial, or the current through the inductor, is going to be the final current, 20, plus the initial, 5, minus the final, e to the minus t over 80 milliseconds. So it's going to be 20 minus 15 e to the minus t over 80 milliseconds. And this is all in terms of amps. Okay, now to find the voltage through the capacitor, it's going to be equal to L di dt. So we're going to multiply 80 millihenries times the derivative of the current. So when I differentiate that guy, I get 0. When I differentiate this guy, I'm going to get minus 15, and then it's going to be multiplied by minus 1 over 80 milli, and then it will be multiplied by e to the minus t over 80 milliseconds. And this will be in units of volts. So this guy is going to be, yeah, we have the 80 millihenry divided by the 80 milliseconds. And so this is going to be 15 e to the minus t over 80 times volts. So there's the voltage across the capacitor. There's the current, or voltage across the inductor, current through the inductor. All right, let's do this last final thing. Okay, so again, when we want to find the current through the inductor. So I1 here is going to be I final plus I initial minus I final, e to the minus t over tau, and tau is going to be L over R Thevenin. So we need to find the initial, final, and the time constant. So the before, I guess, before the switch is thrown, it's been there for a long time. So what we would do is to find the that initial current. We think of this as a wire. So the circuit looks like, 9 volts, 15K, 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 and a wire. And we want to find this current. So we could do a source transformation. So we're going to have 9 divided by 15K, and then we're going to have 15K in parallel 15K, and then another 15K here, and we want to find that current. So these two guys are going to be 9 divided by 15K, and it's going to give us half of that, right? 7.5K. And then another 15K. We're trying to find that current. So we could do the source transformation back. And we're going to get 9 divided by 15K, and this is going to be multiplied by 7.5K. So that's going to be what? 4.5 volts. And then we have 7.5K, 15K, and the current I. So I initial then is going to be 4.5 volts divided by 22.5K. So 4.5 divided by 22.5, 0.2 milliamps. That's going to be the initial current. Now to find the final current, we open this guy, and then the current will actually, all flow and drain out of those resistors. So in the end, I final is equal to 0. And to find the Thevenin equivalent, we open this guy up at the end, and we're going to find, the Thevenin equivalent looking in, which is going to be 30K. 30K. So that implies that tau is going to be 30 millihenries divided by 30K ohms, which is going to be 1 microsecond. Okay, so I1 then is going to be 0 plus 0.2 milliamps e to the minus t over 1 microsecond, and that's all in terms of milliamps. Okay, so that's I1.